So it's a great pleasure to introduce Jae Hee Lee from Stanford, who is going to tell us about quantum power variation.
Thank you for the invitation. It's a great pleasure to be given an opportunity to speak about this work. This conference. Today, the work that I'm going to report is part of a larger program where we're studying arithmetic aspects of mirror symmetry, in particular characteristic P and p-adic aspects of the story. Most of what I'm going to talk about today is joint work with Shaoyun Bai, but also my understanding of the subject has benefited a lot from talking to many other people, many of them are in this audience. So I hope the relationship will be clear soon. So the thing that I'm going to talk about is the characteristic P part of this story, and in particular, certain operations that you can put on mod P loop equivariant quantum cohomology. Two things that I'm going to talk about are the things in the title, the quantum power operations, and the p-curvature of the quantum connection. So let me start by introducing a little bit about this p-curvature, which I think also featured prominently in Simon's talk. So classically, we have this quantum cohomology, which is a deformation of the usual cup product that you have in singular cohomology. We introduce this Nabokov ring, and then you count certain three-pointed genus zero curves to define the structure constants for this new operation, and that deforms the classical cup product, and we call this quantum product. And you can also lift this to a certain operation on equivariant quantum cohomology, so S1 equivariant cohomology. So whenever you have a divisor class, so something in H over 2, then there's a corresponding operator on the non-equivariant thing, which is just taking the quantum cup product with this divisor class. You can try to lift this to the S1 equivariant quantum cohomology, but there's no kind of actual ring structure on that module. So what you do is you introduce this Nabokov derivative, which is indexed by these degree 2 cohomology classes. They act on the Nabokov parameters, which I'm denoting C to the A, where A is some degree 2 homology class, and it acts like something like a logarithmic derivative. So it's the eigenvalue given by the intersection multiplicity of this degree 2 homology class, degree 2 class. So this is the part of the small quantum connection. Consider that part of it. And T is what's often just denoted U is the degree 2 loop equivariant pattern. So this is a lift of the quantum cup product in the sense that, again, this S1 equivariant thing on the top row doesn't have this ring structure, but it has this next best thing, which is this quantum connection operators. And upon forgetting this S1 equivariance, you can specialize the parameter to 0, you have this commutative pattern. And what I'm interested in is certain characteristic P aspects of this operation. So in particular, if you use the symplectic topology approach to Gromov-Witten theory, then in fact, you can define the structure constants that you use to define these quantum product and quantum connection over the integers or over fields of positive characteristic. And that's something that actually, at least with the current technology, uses the symplectic topology approach to Gromov-Witten theory. In general, these moduli space of genus zero curves have certain stabilizers, and just using the algebra geometric framework, it seems difficult to me, at least to me, how to define these FP value Gromov-Witten theory counts. So you really need symplectic topology to discuss these arithmetic aspects that we'll talk about today. So there are certain situations where you can do this. Usually assume some kind of sufficient positivity for your target symplectic manifold. Here are three cases that would be relevant for today's talk. The first case is when it's Calabi Yau, closed with Calabi Yau. The second case is when it's closed in monotone. And the last case is something that has more relationship with representation theory. So when I have something called the conical symplectic resolution, which for now is some kind of a non-compact Calabi Yau, but specifically is holomorphic symplectic, in all of these cases, the last one being a little bit more difficult due to the non-compactness of the target space, you can define these for within theory over the integers and for the FP value counts and try to study the quantum connection positive characteristic. So one way that you can naturally get these mod P quantum connections is to consider the discretized loop rotation action, which is considering this cyclic subgroup of the S1 action generating the loop rotation. So the quantum connection, which was defined on the S1 equivariant quantum cohomology, was linear over the equivariant cohomology ring of S1, which had this degree 2 generator that I was calling T. But if you work with the subgroup CP, then this is what you get over the integers. And if you invert the loop parameter, then you naturally get this ring that's linear over FP because in higher degrees, this group cohomology of CP has this FP. So what's more often done is you just work with you start from the field with positive characteristic or FP as your base commutative ring, and then the equivariant cohomology of CP over that ring it has 2 generators in when P is greater than 2. So T is the same T that we saw before. It's the thing that's coming from S1. There's extra 1 odd generator that I'm calling beta in degree 1. And if you work with CP equivariant quantum cohomology, then this thing will be linear over this ring with FP P theta, which is the group cohomology ring. CP and FP coefficients, and you will naturally have the quantum cohomology, which is defined over FP, and the quantum connection will still give you an operation like this. So right now it's just the same quantum connection, just extended linearly with respect to this extra parameter beta, but now it has the property that's flat connection and characteristic P. So if you have any characteristic P connection, there's a very classical invariance called the p-curvature. And what the p-curvature is the following. So if you think of the connection as something as giving maps from, if you have connection on some vector bundle, consider that as a map from vector fields on the base to endomorphisms of the bundle given by the equivariant derivative, then in characteristic P, these vector fields actually have an extra structure other than their usual Lie bracket structure. So if you take any vector field or derivation, then in characteristic P, if you iterate this vector field P times, then even though it looks like an order P operator, it actually still satisfies the line constraints. You get another derivation. And the usual curvature, you can think of this as an obstruction for the covariant derivatives to preserve the Lie bracket that you have in vector fields. And it's in 2 form in particular, it takes in 2 vector fields. And the p-curvature is an analog of that, which exists in characteristic P, which is now 1 form, and it takes a vector field and measures the failure of your covariant derivative in characteristic P to preserve this extra P power structure that you have. And the striking thing is that even though it's defined in terms of these iterations of the connection, it's actually linear at the point. So for the quantum connection, which we defined in earlier slides, the p-curvature has the following form. So it's now with the p minus t to the p minus 1 nabla p nabla b. And those extra factors of t to the p minus 1 come from the fact that the quantum connection is not the connection in the usual sense, but it has this extra parameter of t in front of the vector field. So it's like a t connection. So that explains this t to the p minus 1 factor. The reason that you get the same vector field on the second term is that if you in characteristic P, this intersection multiplicity is an integer, so if you iterate this vector field P times, which maps by this eigenvalue, then it will give you the same vector. So that's the P curvature of the quantum connection, which is just something very canonical that you get when you consider this discretized computation to try to limit cap products, quantum product to CP equivariant. But there's another operation that naturally exists in symplectic topology if you consider this discretized loop rotation and quantum topology. And those are the quantum Steenrod operations, which I would like to call now. So again, let's fix a prime. Doesn't have to be greater than 2. You can also do this for p equals 2, but this is just for my convenience. And if you work with FP coefficients, then just like how you would define a quantum cup product, you would first look at the classical version of this. So the singular cohomology is general, always a graded commutative ring, but if you work with this FP coefficient, then this module carries extra structure. Classical topology is the Steenrod operations. It has a little bit more structure. And the way the Steenrod operations are defined geometrically is the following. This is the original definition by Steenrod. So there's something that we call the total Steenrod power map, and it's defined as follows. So you take this cohomology class in FP coefficients, and then you take its people tensor power, which naturally lifts to a class creating CP equivariant cohomology of x to the p, because the thing that you get is naturally symmetric under the cyclic permutation action that you have of CP on x to the p. And then what you can do is you can pull back by the diagonal inclusion of x into x to the p. So you're multiplying these classes together, and by the Q-net formula, what you end up with is a power series in these equivariant parameters t and theta with coefficients in the original cohomology ring with FP. And the coefficients that you see after in this power series, or by degrees and some polynomial, the coefficients that you see in this expansion is exactly the classical Steenrod operations applied to your, up to some sign, it's the Steenrod operations applied to your cohomology class. So you can think of this as a kind of a generating series for all the Steenrod operations applied to your class at once. And one way to think about this is kind of a topological version of the Frobenius map, taking an equal copy of the same class and then you multiply them together. It's like a covariant version. And analogously, how you would think of the quantum cup product as a certain deformation of the classical cup product using constant genus zero curves. Fukaya introduced a quantum deformation of these Steenrod operations, and the theory was mostly developed by Nicholas Wilkins. And these quantum Steenrod operations are the extra operations that you get in FP value CP equivariant quantum cohomology that I'll talk about today. So it's slightly more convenient. It's a reformulation due to Seidel and Wilkins. It's slightly more convenient to rephrase Fukaya's construction as a collection of operators that are indexed by these FP cohomology classes. So for each B, which can be any degree cohomology class in FP, you get an operation called Q sigma B, which is now a linear operation that acts on this, say, CP equivariant quantum cohomology with FP coefficients. And the curve, the genus zero, this operation will be defined in the usual way. We want to look at some moduli space of curves and use the evaluation maps from that moduli space to define a certain correspondence between quantum cohomology. And the curve that is relevant for defining these operations have the following curves: a copy of a parameterized P1. And you're looking at this curve with the discretized loop rotations. So it's like a CP symmetry. And the curve has P plus 2 mark points, one input mark point at 0, one output mark point at infinity, and P more mark points along the roots of unity, along which you put this instance constraint, B, for indexing your operator. And then you use the evaluation maps at 0 and infinity to define the corresponding. And this is a reformulation of Fukaya's original construction in the sense that if you apply this to the unit class in cohomology, you just get back Fukaya's quantum Steenrod operations, the quantum Steenrod total power. And if I call the non-core parameter Z, if you look at the classical part of this operator by setting all the quantum parameters to 0, then this linear, the action of this linear operator is the same as taking the cup product with the total Steenrod power of B. So that is the property that justifies the name quantum scalar operations. And you can also try to set these CP covariant parameters to 0. So that corresponds to forgetting the fact that you're trying to work CP covariantly on this moduli space. By the usual degeneration argument, you can show that that's the same thing as taking a p-fold iteration of the quantum coproduct of this class. So these are some basic properties that these operations satisfy. And the key property that Seidel and Wilkins proved in their paper is that these are actually covariantly constant. So the operations that these quantum zero operations that you get by counting these CP symmetric curves actually commute with the quantum connection. So in particular, this is a certain differential equation that's satisfied by this matrix Q sigma V, if you wish. But because we're working in characteristic P, the usual kind of order by order algorithm of determining this matrix from the constant term wouldn't work here. So this, if we were working in characteristic 0, this would actually just determine the quantum zero operations from their classical part, and it can work order by order. But in characteristic P, you can't do this. So in fact, the quantum zero operations are quite difficult to compute for exactly this reason. And another thing that they prove in the paper is that the quantum zero operations give you a certain algebra action of quantum cohomology on this CPA covariant quantum cohomology, in the sense that if you try to compose two of these quantum zero operations, then the result up to some sign, which if you're only dealing with even classes, you could ignore that sign, corresponds to the taking quantum zero operation with a class given by the quantum coproduct of the two. And this is called quantum Cartan relation because if you specialize the quantum parameters again to 0 to get their classical counterpart, this recovers the classical Cartan relation that the power operation satisfies. So these quantum zero operations are the second set of characters that play a key role in this way. I'll try to state my result. So this is probably the most important slide in my talk. So if you look at these two operations that we had, the p-curvature of the quantum connection, which is just canonically defined by the discretized lubrication, versus the quantum scalar operation, then you observe striking similarities. So if you take this class B to be something coming from an H/2 class, so that you can consider the corresponding quantum connection, then if you look at the form of the p curvature of the quantum connection, then this exactly resembles the total Steenrod power of this degree 2 cohomology class. So if you take a degree 2 cohomology class, you want to compute the total Steenrod power, you're trying to compute all the Steenrod operations applied to this degree 2 thing. There are essentially two operations that you can consider, which is the p-fold Steenrod power, just taking the class to its p-fold cup power, and the other Steenrod operation in this case just gives you that. Usually there's one more class corresponding, one more term in that generated series corresponding to the action of the Bochstein on this cohomology class. I'm assuming that the class lifts to integral class so that that actually vanishes here. But this appearance of that type of expression, or Schreier type expression, in this topological context is really the thing that makes this whole story work. So just from this observation, you can bootstrap the following. So if you consider the p curvature, and then you set the quantum parameters to 0, then the p curvature reduces exactly to the operation given by taking the cup product with the total Steenrod power. And by this property that we discussed earlier for the quantum schema operations, the quantum schema operations also exactly satisfy that property. And if you take the covariant parameters t and theta to be 0 on the side of p curvature, again, the setting t equals to 0 will kill the second term, but even the first term, the quantum connection is T del plus this operation given by quantum co-product of B. So if you set T equals to 0 on the p curvature side, that also gives you the same p-fold compound. Yeah.
So like there's like both deformation, direct differentiation in the other directions.
So if you want to consider, well, at least in the way I think the bulk deformations are usually written, there are the denominators, or big one. So it's not immediately obvious to me how to define, say, like the big one.
Yeah, I was wondering what.
Yeah. I think that's a very interesting and important question. Yeah, I have a good answer at the moment. Right now, I'm just taking the small quantum connection for these degree 2 classes. Yeah. And also, p curvature satisfies this covariant constancy property for the obvious reason that this quantum connection is a flat connection. Some polynomial expression given in terms of the quantum connection, so it will also be covariantly constant, just like. So now I'm ready to state my main theorem for today. So if we take X to be a closed Calabi Yau threefold, so that's an example coming from the first category of the three cases where I can define this p value for coefficient invariance. If you have a closed Calabi Yau threefold, then if you take this degree 2 homology class, which comes from an integral class, then these two operations are actually the same. So again, the reason this is quite difficult is because the quantum Steenrod operations are generally extremely hard to compute. Again, the covariant constancy relation does not determine that operation. And moreover, there's no algebra geometric definition to help you compute this thing. It's defined in terms of some perturbed Jae holomorphic curve equation where the perturbation data is parameterized over some classified space of sigma p. So it's a very, in general, a very difficult problem to compute the left-hand side of this. So that's essentially why the properties of both just don't determine this. So I would like to say a few things about what the theorem says. So again, the theorem, this equality can be read in both directions. The one direction, it's a computation of the quantum Steenrod operations in the sense that the right-hand side is just the p curvature is determined by the quantum connection. It's basically, data on the right-hand side is ordinary over any of these schema moduli spaces. And by these two reasons that I was discussing, the quantum Steenrod operations are generally very difficult to compute, but this at least gives you a computation in all degrees, which doesn't depend on this covariant constancy. But on the other direction, this is something that gives you a natural or moduli space description of the right-hand side. So the right-hand side, the p curvature was, the quantum connection itself is defined kind of enumeratively, but the p curvature is given by something as iterations of this operation, especially with this non-derivative term in there. But now we are identifying that with the quantum Steenrod operations, which have all these nice properties that Seidel Wilkins proves. So that can be useful to studying the p curvature of the quantum operations. So I'll show you an application like that later on as well. And the way that we prove this theorem actually produces very explicit formulas for both operators in terms of genus zero property. So I'll comment on the proof in the next slide, but the point is that this actually gives you a very explicit computation, just set of actual power series of off-guard variables that you can write down, and it's very concrete. And about this assumption that this B lifts to an integral class, this, again, the structure of our proof shows that this only affects the constant term. So the only reason that we put this in here is because the constant terms cannot be different on both sides. If you have some torsion class with Box-Stein instance. I think Zygmunt might talk about this phenomenon a little bit tomorrow. But essentially, it says that the purely quantum parts of both operations are also the same. So So that's the reason this mechanism is there. And for most Calabi Yau threefolds, this is actually true, that the fact that there's no torsion class in H/2. So and you can actually lift everything to H/2. So it's not a very strict condition. It's close for almost all the time. So you might try. Okay. And finally, this result is quite complementary to these other non-commutative categorical approaches to a similar type of problem, which featured in Simon's talk and also part of what Simon will talk about tomorrow. And I think our result is complementary in the sense that there's these explicit formulas that we can extract out of our proof, and this can let you do a lot of experiments with these numbers that we get out of this. On the other hand, I think these non-commutative approaches might possibly provide a more conceptual reason why you should expect a relation. Okay, so let me comment a little bit about the proof. So the proof is inspired by Parker's proof of the integrality of logarithmic variance for Calabi Yau threefolds, and uses their cluster formulas. So this is a version of like a structured theorem for the curves in Calabi Yau threefolds. And the upshot is that using this formula, you can reduce everything to a certain one local computation for this target Calabi Yau threefold geometry, which is given by this total space of O-1 plus O-1 over 2. So how is this achieved? So we kind of rough sketch of what the cluster formalism gives you is as following. So if you first fix some energy bound, then you can choose after you choose that energy bound, you can choose some J such that all simple curves that you have in this Calabi Yau threefold are destroyed, embedded, and transversely cut out. But the images of these simple curves may not be isolated. What can happen is that there can be accumulation points in the sense that the simple curves of higher degree may converge to a multiple converse of other curves. However, what the cluster formalism tells you is that there are finitely many curves that you can choose, such that if you look at their epsilon neighborhoods, which are called clusters, then the union of all of these clusters will give you will contain all the curves that you have in Calabi Yau threefolds. And moreover, each cluster gives you a open and closed component of the moduli space. If you look at the moduli space of curves and look at the part of that moduli space whose underlying curve is in one of these epsilon neighborhoods, then that gives you an open and closed subset of the moduli space. In particular, the enumerative content of these moduli spaces, things that count these curves, can be decomposed into these clusters. And as we deform these almost complex structures near each of the simple curves that we see, near each of these four curves, then the cluster counts undergo some wall crossing. The point is that the cluster counts remain the same up to having maybe more clusters whose four curves have larger energy. So you get, in the process of deforming everything to be this complex structure of this particular local model, O-1 plus 1, you can introduce more clusters, and the core curves of those new clusters can have larger energy. But we have fixed a particular energy bound. So if you iterate this process for the new clusters that you get in this process, and then at some point, these energies would get larger than your energy bound. So you can at least say that everything below this chosen energy E, you can just reduce everything into a sum of these counts coming from one computation. And you can induct on E by choosing a large. If you want to compute some generating series with non-power variables, you just choose a larger and larger E, and if you can show that two approaches.
What's happening on this picture?
Yeah. So this is the picture from Parker. So this is a picture for what this kind of outlines telling us. So you should think of the horizontal axis as the parameter where we deform the almost complex structure from from whatever we initially had to this elementary almost complex structure, such that it agrees with the integrable complex structure that you have of the standard model. But in this process, we fix the complex structure at the core curve. So the core curve remains J homomorphic throughout this process. And this gray this gray tubular neighborhood around this core curve are these clusters. So as you deform the almost complex structure to this standard local model, what can happen is that there can be more clusters that are born and disappearing, but all of these have higher energy than the energy of this core curve in the start. And iterate the process to include these new clusters. Yes, and repeat this process.
So what's a cluster? What's
So cluster is an open and closed subset of the space of all subsets of X. You should think of it. One way you can think of it is it's like a neighborhood, epsilon neighborhood of a chosen core. So you have one J homomorphic curve. You look at some epsilon neighborhood around that curve in X. There can be these higher degree curves converging to a certain model cover of the core curve, but eventually they will be these epsilon neighborhoods.
So the curve is a -1 curve at this point?
So after you deform it to a standard complex structure, then it would be this local P1. The P1 is better than P1 so at least lower. So the upshot of all this is that the computation is reduced to the case of this local P1. And this local P1 case, again, the quantum zero operations are very difficult to compute. So this is the most one of the most technical parts of the proof. But one can actually compute all the quantum zero operations for this one particular target geometry, and by using a kind of alternative description of your multiply space. Proof goes through the outline given by Voisin for proof of the celebrated multiple cover for If you adapt that proof to the Calabi setting, then you can actually compute the quantum zero operations for this one particular target geometry. And what you find is that for this local P1, the two operations actually do agree. And the counts that you get out of this are given by very explicit rational functions. So f of z, the z over 1 minus z, that's the celebrated Yukawa length, the generating series for 3-pointed with invariance. And delta is just my notation for this logarithmic derivative, or the Novikov derivative in this case. And phi z is some rational, some power series again, which satisfies this property that it's like a third antiderivative of f of z minus f z to p. So in the end, it kind of the computation is hard, but if you do the computation, this is a very explicit set of numbers that you and in this case, there's one can actually verify this Costas formula, the expectation that Simon has discussed, that these quantum zero operations or these quantum power operations, they can be recovered from a Frobenius explicit version of the usual quantum cup product conjugated by this Cartier isomorphism. So this Cartier isomorphism is not something that we know how to geometrically construct. That's sort of the key obstruction in making conceptual progress. But for this particular example, Kontsevich, Schwarz, and Golovotsky, one can extract, one is that in this case, one can extract this Cartier, the matrix for, and at least the linear operator, the matrix that this Cartier isomorphism should be, even though we don't know how to construct it geometrically. And then if you compute what the Katz's formula, Cartier's formula suggests, in this case, you see complete agreement. Yeah. So maybe that's what I want to talk about to prove in the case of Calabi Yau threefolds. In the remaining time, I would like to explore some other directions. So again, there were these different cases where we can define this p-value Gromov-Witten theory, and I'd like to survey a few work and also discuss some other work with Shaoyun, which develops those other avenues. In the case of the monoclone symplectic manifold, this is the theorem of Seidel and Cormeliano, that the quantum serum operation in the direction of C1 is the same as the p-curvature. Again, in the direction of C. It's like a very small quantum connection. But again, this for monoclone symplectic manifolds, you can define quantum serum operations as a quantum connection over Fp with no problem. So the statement makes sense, and we can try to prove it. And a slightly weaker version of this statement, which is that the difference of these two operators is nilpotent, was used by Zhihong Chen to show this unramified exponential type conjecture for the singularity of the small quantum connection of a monoclone manifold. So these are results that leverage this identification of quantum power equations of p-curvature. In particular, the key thing that's used by Chen in the proof is this local mononomial theorem of Kotz, where this nilpotence of psi should be this F, the p-curvature. So there's a theorem of deep theorem of Kotz, which gives you a criterion for detecting singularity types of connections in terms of nilpotence of the p-curvature. And how this identification helps such checking something like the p-curvature is nilpotent is again by identifying it as the quantum serum operation, you can show that these iterations of the p-curvature on the right hand side are the same as the iterations of quantum serum operations on the left hand side. But the quantum serum operation by this quantum Cartan relation, you can identify iterations of quantum serum with quantum serum on the cup product, quantum cup product of the class that we're trying to take the operation. Yeah, so I wanted to talk about this because I think it's a remarkable theorem, and it's also a application of this characteristic P story to characteristic zero symplectic topologies. Even if you don't care anything about this arithmetic story, this is an indication that this avenue can be helpful for studying. Okay, so in the remaining time, I would like to discuss a little bit more about this third case of the story for these conical symplectic resolutions and the q-deformations of the story we have been talking about. So another class of examples for which these quantum serum operations can be studied are these certain complex symplectic manifolds coming from representation theory. So these are these conical symplectic resolutions, and what these are certain non-compact holomorphic symplectic manifolds, such that their resolution of singularities of their application. And the conical part of this says that these are actually equipped with an additional contracting C star action, which retracts everything to a complex subset. And these spaces naturally arise in representation theory. In particular, they're responsible for their role in this 3D mirror space. An example of these target manifolds would be something like the cotangent bundle of P1. That's the thing that resolves the nilpotent cone in SL2. It's the holomorphic cotangent bundle, which naturally carries the holomorphic standard symplectic form. But we're considering it as a symplectic manifold for doing Gromov-Witten theory by taking its symplectic form to be the Kähler form for which the zero section is symplectic symplectic. And this again comes with these kind of extra structures, which is this action of a Hamiltonian torus and another C star action, which contrasts everything to a compact subset. In this case, the C star action is given just by fiber dilation, and the other Hamiltonian action is given by the natural S1 action on the base. extended to a Hamiltonian at different points. Okay, and one case that we were actually the first case that we were able to verify that these relationship between quantum power operations and p-curvature was actually in this context. So if you have some conical symplectic resolution with certain technical conditions, then you can show that for these equivariant generalizations of the quantum serum operations incorporating these Hamiltonian torus symmetry and the scaling symmetry, dilating symmetry, are equal to each other. And so in the Calabi Yau threefold case, we had this direct geometric proof by just computing everything for this local P1 and bootstrapping it using cluster formalism. The proof of them in the monotone case is a kind of a clever degree argument. The proof in this case, so there are like these three iterations of the same statement, but the proofs are all different. I think that's kind of an indication that we should really try to understand this a little bit better. But in this case, the main proof idea is to show the compatibility of both operations, particularly the quantum serum operations, with the shift operators, which were featured in Dan's talks. So these quantum serum operations in this representation theoretic context also makes contact with this 3D mirror symmetry story and plays some role. But that's not the part that I would like to discuss further in today's talk. I would like to focus on this other direction, which is the q-deformation of this story, which exists for these conical symplectic. So a large class of these conical symplectic resolutions, there's one class coming from these Coulomb branches that were showing up in Dan's talks, but another large class of examples come from things called Higgs branches, which are certain hyperkähler quotients of a cotangent bundle of some complex representation of a compact lesion. If you have some compact group G acting on a complex representation N, you can take T star N and then take the hyperkähler reduction of that, and that gives you a huge class of these conical symplectic resolutions that was discussed on the earlier slide. And for such targets, in particular things that are given by certain target symplectic manifolds which admit a certain presentation as a GIP quotient, there's a very well-developed theory of quantum K theory due to Kunkov's school, which uses stable fuzzy maps instead of the stable maps that we used previously to study quantum string operations. So here now we're kind of switching gears. In quantum K theory, there's no longer this problem about denominators. The values that you get are naturally integral anyways. So you can work in this algebraic geometric setting. And if you work with quantum K theory of these, say, hyperkähler quotient, symplectic resolutions given by hyperkähler quotients or GIT quotients, then everything that we said today actually admits a K theoretic generalization. So here's a little chart to compare the two cases. So quantum cohomology additively is this just the additive cohomology joined with these quantum parameters, which is not nothing. And the quantum K theory setting is also the same. You consider the K theory join these quantum parameters. The loop parameter, this key thing that we were discussing, was a generator of the degree 2 part of the equivariant cohomology of CP with their P coefficients. In particular, it was additively quotient. You multiply it by P, you get 0. In K theory, what you get instead is you work with CK equivariant cohomology, where K can be any integer now, it doesn't have to be a prime number. And the loop parameter, which I'm calling Q, is multiplicatively quotient. So root of either. Take a K power, you get 1. In quantum cohomology, we have the quantum connection, which is the differential connection. So there's these Novikov derivatives, partial A, which acts on the quantum monomials by these eigenvalues of intersection multiplicity. In the K theory case, instead of a differential equation, you get a Q difference. And here are the operators, instead of being indexed by degree 2 cohomology classes, you can index them using line bundles, and you can Q shift in the direction of some line bundle by multiplying the quantum parameter with this phenomenal Q to the L-pass. And in cohomology, the quantum serum operations were supposed to be deformations of these classical Steenrod operations that you have in topology. And in K theory, there's also an analog of Steenrod operations, Adams operations. And Adams operations are also examples of what we call power operations. So they fall into, in algebraic topology, they fall into the same category of these schema operations. And they're defined in almost the same way as we define this schema operation. So take some K theory class, and then you take the K-fold external tensor product of that. That gives you some genuinely CK equivariant K theory class in X and K. And then you can again pull that by the diagonal, which is again CK equivariant. So this. And the place that you land in is, because CK acts trivially on X, the place that you land in is the K theory of X, where Q is this loop parameter, the generator of K theory, the representation theory of CK is something that's multiplicatively quotient. You further pass through the quotient of the K cyclotomic polynomial, and that's like setting Q to be exactly your K. So if you do this composition, then you get these Adams operations, and you can think of them as K-theoretic analogs of Steenrod operations, which are again defined by the exact same recipe.
So, yeah. This notation, what's capital P?
Capital P is the K cyclotomic polynomial. So it's a factor of this q to the K minus 1. But if you quotient out by this ideal, then it's like setting Q to be the primitive. It's specialization. Again, the quantum connection that we had in the cohomological setting now becomes the quantum Q difference connection in K theory, where you try to write down what the equation would be, it would be given by something like this. So J is the thing that you're trying to solve, and the Q shifting in the direction of this line bundle L is given by some operation, some matrix, say MLZ, acting on this quantum. And another theorem with Shaoyun is that for these class of targets for which you can define these stable quasi-map counts, then you can actually define a deformation of the usual Adams operations to quantum K theory. So again, it's quantum K theory where you specialize this Q to this K theory of unity. And this is a quantum deformation of the Adams operations in the sense that if you set all the quantum parameters to 0, then you get this tensor product with the classical Adams operations applied to this line L. And moreover, this is again covariantly constant in the sense that this operation, Q psi k, the quantum Adams operations that we define, also commute with the actual. In this case, you actually have this analog of the story that we're trying to tell, this quantum power operations being equal to p-curvature that also admits this K-theoretic generalization. So on the left-hand side, you have this quantum Adams operations in the direction of this line bundle L that we defined. And on the right-hand side, this is a iterated product of these quantum Q difference matrices, all shifted by a particular power, all Q shifted by a particular power. So we take this operator ML, and then you Q shift it once, you multiply that, and then you Q shift it twice, and you multiply that. And if you take this iterated product, the thing that you see on the right-hand side is the correct analog of this p-curvature operator that we defined in the case of differential equations in the setting of Q difference. And it's the theorem that we proved in this setting that both operations are the same. This is like the fourth iteration of the same statement that we're trying to prove, and it has again a different proof in this case. And the proof of this statement in this K-theoretic setting is actually given by some degeneration. We call it usually like a TQFT argument, something topology. So one can actually just use a ordinary degeneration argument to identify these two. So something like that is not, at least as far as I can see is not necessarily available in the setting of quantum cohomology.
So what that you're degenerating?
Degenerate means I look at the moduli space, which is responsible for this quantum atoms operation, and that again has these kind of insertions of these line bundles that decay through the unity. But again, it's given by some counting and parameterized copy of P1 with k plus 2 markers for the k markers are at the roots of unity on the equator. And then you can look at the moduli space and you take some deformation where you can identify the moduli space with the moduli space that defines the counts on the right.
Are you moving in the moduli
Yeah,
for the corresponding performance theories? Okay.
So the thing that defines the quantum atoms operations are curves that look like this, say quantum Steenrod type moduli space where we have k insertion. And operations that you get by counting such curves are the same as the operations that you get by counting. So if this is considered as some k-symmetry, the operation that you get from counting such curves is the same as the operation that you get by counting curves with different configurations where the k insertions are given us a smaller circle. And as you do this degeneration, you look at what happens when all of these k points collide at this point. That's exactly the thing that will compute the right-hand side of this equation. But you can't do this for quantum cohomology for some reason, and that's again, I think it's an indication that we should try to understand what's really going on here. But in the K-theory case, it's actually a slightly.
You can't do it because of
the quantum connection not having a immediate kind of moduli space description. So each of the factors that you see on the operation on the right hand side is just something that's defined in terms of the geometry. But for the p-curvature, the quantum differential connection, kind of see maybe someone else can. Yes. Maybe an analogous thing that one can say. So even in quantum cohomology, you have the quantum difference. When you have some Hamiltonian torus symmetry on the target, you can define these shift operators that will make sure that can't stop, and that defines you a difference connection instead of differential connections. You have these shift operators or equivariant sidal operators. And even in cohomology, you have some kind of a difference connection like this, or some choice of co-character torus at X. And what the proof that's analogous to the proof that we're giving here is just the fact that if you take the shift operator in the p-dilated co-character, this is the same thing as just iterating the sidal p times. This is a degeneration, but which you can do because each of these individual vectors are defined first. But for the p-curvature, where the analogous thing is the quantum connection instead of some geometric operator like this, I don't know how so yes, so perhaps we're doing this in this algebra geometric setting, but if one can try to reformulate all our results and reprove everything in the context of something like homotopy theory, this might be another general set. So in the last part of my talk, I would like to discuss some compatibility relation between these quantum atoms operations and quantum schema operations that have homology. So there's some homotopy theoretic heuristic comparing this CP equivariant K theory and CP equivariant cohomology, which leads us to propose the following. So what you do is you now expand in this parameter q minus 1, where q is the loop parameter that you have in K-theory. You can expand that q minus 1, you set that equal to beta times t, where beta is the thing, it's the Bott element in K-theory, and t is the same exponent provided. Then you expand this quantum atoms operation, which is some expression that involves these q's. If you try to expand it near this q minus 1, then what you would get is you would get these large series involving betas and t's. And the conjecture is that if you take this class of a line bundle, which defines you in particular a quantum atoms operation, then it's related to the quantum schema operation the following way. So if you take these quantum, now you take the integer k, which is relevant for defining quantum atoms operations, to be a prime number p, and then you look at the quantum atoms operations in this direction of L. Then this, if you expand this in this parameter beta, the Bott element, then initially you have just the identity matrix 1, and then the first thing that you see is in this power beta to the p. And the claim is that the coefficient in that beta to the p expansion is the quantum schema. So implicit in this is the claim that if you take this CP covariant K theory and you pass to the associated gradient of this beta at filtration, then you get this FP value. Okay, so this can actually be verified using this description of quantum atoms as the Q difference p curvature. In these settings where we know that the quantum schema operation is equal to homological p curvature. So those are the cases that were featured in my previous theorem. So for certain conical symplectic resolutions, which satisfy the technical conditions that I had earlier, we know that the quantum schema operations are the p curvature. And one can verify the conjecture like this for those examples. Both in this description, the right-hand side will generate to an analogous version of the right-hand side in this expression involving p curvature, the photon betas. And again, trying to prove this using actual comparison of the two settings, it seems very difficult because in quantum atoms operations, we define these using stable quasi maps and algebraic K theory, whereas for quantum schema operations, it's just the usual p values and get homology. So I think one way to approach a certain conjecture like this may be just try to define quantum atoms operations in quantum K connection, just in the proper setting of thermal theory, where we can actually work with operational K functions. Okay, so that's all I want to talk about today. Thank you.